This is something I do in collaboration with a number of people that you see up there. There's Erik van den Eynen at Gran Institute, Jesse Dorrestein, my PhD student in Amsterdam, and 3 people from KNMI and Delft Technical University, Pier Siebesma, Harm Jonker, and Frank Selten. So I want to present here some ideas on a particular take on stochastic parameterization that we're working on, and I've tried to summarize this approach on this slide here, and it comes down to 3 steps. A little different maybe from some of the work that's going on stochastic parameterizations is that this is strongly sort of data-based. We want to use stochastic processes that are really inferred from data in order to inform the sort of the core skill models where these parameterizations are needed. Now we're being a sort of geoscientists means we or you are in a way lucky, because for a lot of processes there are actually models, which is a little different from maybe people working on some biological problems or economic problems, where having models in the first place is a problem. But for us, right, we're somewhat lucky here. For a process like convection, which is what I'll be talking a little bit about here, we do have models that can simulate convection reasonably well. It's just that they have to be resolved on such a sort of fine scale that, as we all know, this is not something you can do globally. But in any case, there are models, and what we propose here is to use those sort of high-resolution process models, if you will, which are most of the time must be used in a kind of limited area mode, simulate the small-scale processes with these high-resolution models, take the data that comes out of that high-resolution model to estimate a suitable stochastic process that somehow mimics or emulates the feedback from the small scales that you need in your parameterization. And what it means to have a suitable stochastic process, how we see that, I'll discuss later on. And then once you have that stochastic process, you use copies of that at different spatial locations, different GCM model columns, to use it as a parameterization in, for instance, a general circulation model. Okay, so one process that we're particularly interested in is that of shallow cumulus convection. And as is well known in GCM model columns, you need to parameterize the vertical turbulent fluxes of heat and moisture that are induced by the convection, right? That must come out of a parameterization. So what we do here is use a high-resolution model, which is a large eddy simulation model with a spatial horizontal resolution of typically 50 meters. So it's really high resolution. And then, of course, on a limited domain, I'll show you some results later on from an LES simulation, that's an LES model, that runs on a spatial domain of about 25 by 25 kilometers at this resolution of 50 meters horizontally. So the turbulent fluxes that are simulated by this LES model, of course, I would almost say, they depend on the resolved skill state. If you parameterize the turbulent fluxes, of course they're going to depend. Their typical behavior is going to depend on what the resolved skill state in that model column is, and it seems obvious, but it's not so obvious how to design a parameterization, a stochastic parameterization that actually reflects that. Okay, another simpler example is the Lorentz 96 model, which is kind of popular to sort of use as a testing ground for new ideas in this area. For those of you who are not familiar with it, it's You can see it as a one-dimensional model on a periodic lattice. It's nonlinear, it's forced and dissipative. So I've written down the equation there. In fact, there's, if you will, a resolved scale set of variables which are denoted x sub k here, where k is the grid point index, and so it has its own dynamics, right, indicated with this function f. But there's a part to it that comes from small scales, and the Lorentz model, the full Lorentz model, actually has explicit equations for this b, or for the variables that drive this b as well. But of course, the idea here is to try and do without sort of these small scale, in quotes, variables that drive these b sub k quantities, and devise a parameterization for that. And in this model, again, this feedback that I dubbed b sub k here from the unresolved skills it changes over time, and it's also that its behavior is dependent on x sub k. So again, this is something to take into account in the parameterization. So this three-step procedure that I presented in the beginning comes down to the following in this case. So take this high-resolution model, which is just a full L96, two-layer L96 model, generate data with that, and take that data and fit a stochastic process to that data. And that process should depend on the state of x at the same grid point. And then again, use that, once you have inferred that stochastic process, use it in simulation, in sort of low-resolution simulations where you only explicitly resolve these x variables and not the small-scale variables which are denoted y in the full L96 model. Use those stochastic processes to sort of emulate what comes out of the small scales. Okay, so now what does a suitable stochastic process mean? Well, first of all, we assume, so that's an assumption, that it is a Markov process, first of all. So it means that again, if you look at these B quantities, so they're correlated in time, it means it's not, you don't want to do sort of IID sampling, by which I mean that, of course, what you can do is collect a lot of data from your BK, sort of infer an overall distribution for B from it, and draw independent samples from that. But that would not be a stochastic process, right? You wouldn't have time correlation there. So that's something not to do here. You want to model it as a Markov process. Second, it's supposed to be conditional on the resolved skill state, X. So these two properties bring me to this particular sort of model, which is basically the conditional transition probability for these quantities B. And it just says, well, if you have B and X at some time t, then there's a distribution that depends on both for the next time iterate, if you will, of B. So there's this conditional transition probability, right? Without X, it would be sort of a regular, if you will, stochastic process, but we make a dependence on this X. And there are, of course, variations possible. I mean, you can add all kinds of additional conditions. One example being where you also add the time derivative of X at that same moment to it. And of course, you can add more. You can add many conditions if you want, but of course you will need the data to actually infer that particular process. Thank you. Now, how to do that in practice? We do this by treating the stochastic process as being a Markov chain. So that means that the possible sort of feedbacks or values of B, and I'm putting this in sort of in the terms of this Lorentz 96 model, the number of possible feedbacks are made finite. So you have to discretize, because typically B will not, it will not be a discrete quantity by itself. So you have to discretize it somehow, and you can do this in all kinds of ways, and one example being clustering. And once you do that, you end up with this conditional transition probability is then represented by a handful of stochastic matrices, and how many and how big, of course, depends on how many discrete states you want to use for B and also for X. Now, the advantage of modeling this with these conditional Markov chains is that they're very easy to estimate from data, and they're also easy to compute with. So it's really to some extent driven by practical considerations to model this with Markov chains rather than continuous stochastic processes. Okay, so for the Lorentz 96 model, how does that work out? Well, what I've shown here is a scatter plot of this resolved variable x horizontally, and in the vertical it's this sort of feedback from unresolved scales B. And you see all the small dots that's basically a scatter plot that comes out of a simulation with this with the full model. So say if you will, the high resolution model. And of course, if you follow what this full model do, is just move around in this through this point of clouds in a particular way, and to try to capture the way it moves around stochastically is by choosing these black squares. Right, that's a discretization step. So rather than allowing all possible values for B, I only allow these black squares, and right, as you see, for each interval of X, every time there are 4 of them, and basically I just let these B's during a simulation with my sort of low resolution model, if you will, X only model. I let the B's jump between these black squares with a prescribed sort of pre-computed probability distribution that is essentially what is up there. So there's a condition of X, but also its time derivative added to it. Now, if you do that, here's some very briefly. There's a bunch of results in a paper we have on this, but I just want to show you this one: root mean square error and anomaly correlation over time. And as you see, it gives a better performance than using either a deterministic sort of modeling of these B quantities or a deterministic modeling plus correlated AR1 noise. So as I said, but there are a bunch of more results, but I'm not going to show that here, but rather go over to the next topic, which is how to use this for shallow cumulus convection parameterization. And in that case, the high resolution model data comes out of, as I said previously, an ADS model on about a 25 by 25 kilometer domain horizontally. In this case, right, in Lorentz, this Lorentz example, both the subgrid scale responses B and the resolved scale states X at each grid point are scalar quantities. Now, okay, scalar quantities that's one thing to do, but now for actual convection, it gets far more complicated, because these B's, first of all, there's not one of them, but 2, because they're turbulent fluxes both for heat and for moisture. They're correlated both in the vertical and between the 2 of them, right? Okay. Secondly, resolved scale state again is not a scalar, but there are also vertical profiles for 5 different quantities: wind velocities, temperature, and humidity. So it makes it a lot more complicated, right? So we're not dealing with 2 scalars, but with a number of vertical profiles, functions. So to discretize this, we use simultaneous clustering of these heat and moisture fluxes, and the result of that you see here. So in blue, on the left, it's turbulent heat flux. On the right, it's turbulent moisture flux. In blue are sort of observed fluxes from the LES model, and in red are the sort of cluster centroids. And what I mean by simultaneous clustering is that each cluster centroid corresponds to both a heat flux profile and a moisture flux profile, and that sort of takes care of the correlation between the two fluxes. Now, if I take these, so that's after the clustering, we infer all the Markov chains, and if you derive these Markov chains with the sort of observed states of at the result scale, then this is what you get. So on the left is the LES, on the right there's the Markov chain sort of emulation or reproduction of that. And I have to stress that you would not expect sort of a pathwise exact similarity between the two, right? It's a statistical similarity that we're aiming at here. Okay, here is. I have to to stop here. So there's going to be explanation about this figure in the paper that we have almost finished on the cumulus convection parameterization. So here are two references: a paper that's already out a couple of years ago, and a paper that is nearly finished and should be on my website hopefully within weeks. Thank you.
Well, thank you very much. And I think in the interests of time, we should move on to our next speaker, David Nealon. Thanks.
Just a word about our technical issue. The technical issue is with the timer. And so we actually have a stopwatch here that we're using. So after 12.5 minutes, we'll signal the speaker that he's in the wrap-up time. And then at 15 minutes, we'll jump up and down and make all sorts of noise. Okay, so our next speaker is David Nealon. And it's my pleasure to introduce him. He's going to be speaking on informing stochastic parameterization, threshold processes, tails, simple prototypes, and observations. And I'm going to get this up in just a moment, I hope. Voila. Thank you.
Okay, thank you, Cecile. So I'm going to be talking about really two sort of specific subjects within what could be a very large area. I'm going to do some background on some observational constraints on the onset of strong convection that can be interpreted in a self-organized criticality manner, as Alvaro Corral so nicely summarized for us in the previous session. But then going to switch immediately to a very simple stochastic prototype for some of these onset statistics that has to do with finding the simplest model where you think you might be able to get some of the things that we see, and then connect that to long tails in some other distributions. And both of these things will be simple enough that they should be fodder for lunchtime conversation, because there's a couple of things that can be interpreted more than one way. Very briefly, touching on some of the history of stochastic parameterization in an atmospheric convective context. Convective quasi-equilibrium is a term that's been around since Arakawa and Schubert in 1974, describing the fact that you assume that moist convection rapidly dissipates buoyancy, and if you are using this in a convective parameterization, you assume that it keeps you pinned close to onset, although if you assume a finite timescale process for that, there's a strong dependence on what you assume about how that happens. In doing this, you omit a lot of properties that you would find in near such a transition, for instance, in lattice models, including things like power law size distributions, which Alvaro talked about in the previous session. And you also have the fact that the ensemble size of deep convective elements in your typical GCM grid size equivalent box is very small, so you expect to have quite strong variance about the ensemble mean. One approach to dealing with these questions is superparameterization, embedding a cloud model, and then there's been a history of stochastic parameterization, trying to represent the subgrid scale elements stochastically. References to some of them there. Here is an attempt observationally to constrain some of the statistics for observed precipitation in a way that determines a critical value for the onset of deep convection in the tropics. The statistics you're looking at here are a conditional mean precipitation conditioned on water vapor and temperature, which are each a bulk measure through the troposphere, standing in as a proxy for the factors that affect conditional instability of the deep convective plumes. When you empirically determine a critical value for the onset of that process for a given water vapor and as a function of temperature, and you normalize by that critical value, you get a nice collapse of the onset curves. Do we have a laser pointer here, or are we just expected to use the mouse?
It's right here.
Oh, there we go. Thank you. So this curve here is the pickup of precipitation being collapsed for different temperatures. You get a strong peak on the variance, which has interesting scaling properties at the onset threshold. And then here is the occurrence probability, the frequency of occurrence of each water vapor for precipitating points, exhibiting a Gaussian sitting just below the critical point here, but then this switch over into a roughly exponential tail that carries you much more often up into the very strongly precipitating regime than you would expect if you continued that Gaussian. The Gaussian is a sort of a quantification of the quasi-equilibrium assumption that says you do end up sitting below the critical point a lot of time, near but just below. And then this tail is a bit of a mystery that will be one of the targets for simulating. You also get precipitation event sizes that are distributed as a power law, and I'll touch on that again, and Alvaro neatly summarized some of the statistics for that in water vapor. Also relevant for both the pragmatic and the interpretation aspects of this is the fact that the column water vapor has rather long autocorrelation times, whereas the precipitation, although it turns out to be approximately a power law range here, in the range that parameterization formulator thinks about is has a much lower, steeper drop in the autocorrelation. And that's consistent with having a large-scale field involving the temperature and the water vapor within which precipitation is evolving essentially stochastically. Looking at this with a couple of different data sets, what I showed you before was from the Nauru ARM site gauge data, and here is a satellite estimate of the same temporal lag. This involves a clever trick by Beijun Tian, where we're using the satellite crossings to estimate the temporal autocorrelation so you can do spatial things at the same time. This is on a log-log plot, so now you see the approximate power law range and the precipitation estimated from the satellite. And here it is in the optical gauge data with a similar slope, which is relevant since we're mixing those two types of observations. All right, what about a simple model? Now, there's some appealing things if you, for instance, have the analog of a lattice model exhibiting self-organized criticality to these convective parameterizations. But the long tail of the water vapor distribution up in the range above the critical point is not something that appears to have a good analog there. And we've been interested in this from the point of view of what can you capture in stochastic parameterization in the model. So what if you begin with the very simplest system for a tracer Q, which is the column water vapor. So here we're thinking of integrating through the column. And then we're just looking, if you like, at a single grid point as a function of time. So this is just a scalar. You have a source process deterministic, which is like evaporation. And then you have a Wiener process kicking you around that changes properties as you switch from a non-precipitating to a precipitating state. with a stochastic jump process that flips you into your from non-precipitating to precipitating, with transition rates from off to on and on to off that are all specified as function of your water vapor. And since things collapse as a function of temperature, we can do this just for water vapor at the moment and think about the transition there. Now, there's a couple of things going on at the same time in this model, but we can take them apart to see what's important. The transitions are, as you pass a critical water vapor, we've got one in the transition rate, we've got one in the deterministic part of the precipitation rate, and we've also got one in the amplitude of the Wiener process. Sample time series looks, plausibly like the observations in that your water vapor kicks around and your precipitation switches on and off. This is the jump process itself shown here. The precipitation also has amplitude variations. Essentially you're thinking of the water vapor reacting to the stochastic forcing with the sink turning on some of the time. The stochastic white noise kicks are standing in for two things. One is that your precipitation will have a non-deterministic part in terms of what's controlled by the large-scale fields, but also you have large-scale convergence, which is pushing your water vapor up and down. And that's an important part of the atmospheric dynamics that would come in from outside the grid cell, if you like. All right, so a couple of things. We were interested first in looking at the distributions of the water vapor for precipitating points. But here's some things that popped out untuned when we started looking at them. One is if you look at the total precipitation on an event from when it started to when it stopped, this is something that Ola Peters has looked at quite a bit, and down here is a reference to a paper he led showing how similar these statistics can be at different observational sites. I've just repeated the slope from the Nauru observations that I showed you earlier. The power law range that you're happening to get out of this very simple model is much shorter than in the observations and slightly steeper, but it's essentially coming out just from pushing yourself back and forth across the threshold. Other properties that you can see now, the conditional mean here is being controlled by our input assumptions, so we don't get to count that as a success. The variance having that at a peak near the threshold is no surprise either, but I'm listing them there just to note that you get those as you expect out of the system as set up. And then things become a little more interesting when you look at the probability distribution for the water vapor as a function for the precipitating in red, the non-precipitating dashed in blue, or the total here in gray points. You have something like a exponential tail on either side here, and a quadratic, so roughly Gaussian core in the middle. And you can do analytic Fokker-Planck equation solutions in particular regimes to look at the things that in this model contribute to those properties. And then you want to step back and say, okay, but it's a very simple model. What aspects of this do I believe or not believe? And so I'll just show you the ones for the precipitating case. So an equation being worth 1,000 words. Here's the equation being solved. With the Fokker-Planck equation, it has a term from the jump process. It's like a master equation. And then you go into the particular regimes where things simplify. So, for example, if you are in, let's do the high column. Sorry, 2 minutes. Are you serious? Okay. All right. So you essentially find that in the finding the slope for what happens when you're precipitating, but in the low column regime, the jump process is very important to that slope, whereas in the high column water vapor regime, you essentially have the driving noise versus the sink controlling the slope up in that regime there. In the temporal autocorrelation coming up here, this is also a suitable target for analytic work, although we haven't done that. You find that the model, again, is a little steeper than what you found in the observations, but has a very substantial power law range in the precipitation coming out essentially for free, untuned out of this, just from forcing yourself across the sharp onset. And to my chagrin, you can remove the Markov jump process from the model and still obtain that. Now, I want to connect this to long tails and a prototype for tracer solutions that you've seen from Ray Pierre Humbert in stratospheric work, and Berlew and Maida have a very nice prototype for this in terms of just a passive tracer. I'm going to show you some things. We've done this for a whole bunch of tracers in the retrievals in the troposphere. I'm just going to show you a couple of observational results for surface temperature and mention that there's more than one prototype for some of the long tails in these. This is the probability density function of surface temperature, and if you, there's an error bar here for a Gaussian core being simulated by realizations of an AR1 fit to that statistics. And there are these tendency for long tails to stick out on one side in many stations, although it switches from one side to another, depending on where you look in the distribution in your station. So it's extremely common to have departures from this Gaussian fit to the core. And these long tails are going to have severe consequences when you're trying to do quantitative estimates of what happens under global warming. Just noted here, if you do a shift of these distributions, the rate at which threshold exceedances go up for a Gaussian versus these long-tailed distributions is very, very different. And this is something that will be a target in our climate model and represents another target for stochastic representation within our climate models. So, and I'll stop with the summary with two figures repeated from the core of the talk.
In keeping with our intransigent way of keeping our time, perhaps we should continue on to the next. We will have a nice lunch break before we have the poster sessions at 1:40, and let me tell you that we're going to have them there. Now, they're just right outside.
Sorry. And I think once again, for the interest of time, we're going to have to carry on to the last speaker in this morning's session, which is Sergei Crafts.
Hello. First of all, I would like to thank the session organizers, Adam and Cecile, for inviting me to give a talk here. It's very nice to be here. The session was short but very interesting. So this work has been done in collaboration with my students, Nick Schwartz and John Peters. It deals in a way with medium-range weather predictability, and it's based on two major assumptions. The first assumption is that there are some atmospheric states that are inherently more predictable than other states, and the second assumption is that those states are associated with the so-called nonlinear atmospheric regimes. To introduce the regimes, I will follow a presentation, a very nice paper, a 2005 paper by Philip Shura, Neuman, Cecil Penland, and Sardesmuk, in which they introduced the symbolic decomposition of the atmospheric flow into the large-scale, low-frequency component X, and the deviation X prime associated with fast transients, for example, synoptic eddies. And if you write out the averaged equation for large-scale, low-frequency variable, then it will have linear terms. How would I do this? Linear terms, Lx, the external forcing F, which I will assume to be constant, and 3 types of nonlinear terms: the interactions between the components of the large-scale flow, the interaction between the large-scale flow in synoptic eddies, and the interaction between the synoptic eddies. And in the sufficiently stochastic atmosphere, the third nonlinear term can be well approximated statistically as the Gaussian distributed white noise. If, in addition, the terms N1 and N2 are either small or linearly parameterizable in terms of the large-scale variable x, then the distribution of x will also be Gaussian, because it will effectively be governed by the linear equation driven by the Gaussian distributed forcing. In the opposite case, if those terms N1 and N2 are both not small and not fully parameterizable linearly via x, the distribution of the large-scale variable x will exhibit the deviations from the Gaussianity. And those non-Gaussian regions will define our atmospheric regimes, nonlinear atmospheric regimes. In summary, the regimes can arise either due to interactions between the components of the large-scale flow or due to interactions between the large-scale flow and synoptic eddies. Conceptually, this can be visualized using the mechanistic analogy of a one-dimensional model of a particle moving in a potential field subject to the stochastic agitation. And in this analogy, the role of low-frequency variable is played by the position of the particle. The V is the shape of the potential, and the term involving the potential function is the deterministic interaction term. And then there is a stochastic term with an amplitude which can depend on the large-scale variable x. And this parameterizes the interaction between the low-frequency flow and the fast transients. And there are 2 different situations here. In the first situation, with additive noise, which does not depend on the state, large-scale state of the system, we have the potential with 2 wells. And then in the second situation, the deterministic term is linear, but the amplitude of the stochastic forcing is maximum in the location of a stable equilibrium and decreases on both sides of this location. In both of these situations, we end up with an identical bimodal, strongly non-Gaussian distribution, and the modes of this distribution define our nonlinear regime regions in this case. Despite the identical distribution, the predictability characteristics associated with those regimes would be very different. It is intuitively clear that the regimes that arise due to slowing down of model trajectories due to deterministic nonlinearity are inherently more predictable than the regimes that arise due to lowering the amplitude of the multiplicative noise. So what we do in this work, we study the regimes, their origin and predictability by analyzing a long output from a well-known idealized atmospheric model. That's a 3-level quasi-geostrophic model first introduced by Marshall and Molteni in 1993, and it is tuned to reproduce the observed climatology of the stream function at the 3 model levels, but it also has a fairly realistic low-frequency variability. The lower panels here show the leading 2 EOFs of the upper layer stream function in the model, and the first EOF is zonally symmetric and associated with the Arctic oscillation, the modeled version of the Arctic oscillation, and the second EOF is a linear combination of the North Atlantic oscillation and Pacific North American teleconnection patterns. In addition to stream function EOFs, we'll also be computing the EOFs of the zonally average zonal wind, and the upper panels here show the regressions of the zonal mean zonal wind principal components onto the regression of the stream function, onto the leading principal components of the zonal mean zonal wind. And you see that the first EOF of the zonal wind is strongly associated with the first EOF of stream function in the model, but the second EOF doesn't. In the remainder of the talk, I will be looking at the behavior of this model in the phase space projections onto the planes of the two leading EOFs of either stream function or zonal wind. For each state of the model in those phase planes is a point whose x-coordinate is the projection of the state onto EOF1, and one y-coordinate is a projection onto the EOF2. And we'll define the nonlinear regimes in this model as the regions in the phase space in which the persistence properties of the full quasi-geostrophic model trajectories are statistically distinct from the persistence properties of the equivalent linear model driven by the Gaussian white noise. I don't want to spend time on the regime identification methodology here because the results of regime identification do not really depend on the particular methodology you use. In both phase planes here, we find three regimes which are characterized by distinction, statistical distinction between the behavior of the linear model and the behavior of the full nonlinear model. Out of the 6 regimes, only 4 regimes are statistically distinct in the sense that the sets of states that define the regime 1 and regime 2 of the zonal wind or stream function are statistically identical. So we've got 1, 2, 3, and 4 distinct regimes. And we can compute the composite patterns of those regimes by averaging among the states comprising each regime. And here are the regime patterns. The regimes 1 and 2, which turn out to be predictable, are associated with the Arctic oscillation, with the different opposite phases of the Arctic oscillations. And regimes 3 and 4 are less zonally symmetric and have features of the North Atlantic oscillation and the Pacific North American pattern. And essentially, the same regimes in the same model can be obtained using multiple various regime identification methodologies that has been published previously. Okay, now this slide presents the main result of this study. Let's concentrate first on the upper left panel. Once again, we are looking at the behavior of the model in the phase plane of the leading pair of EOFs of the upper level stream function. And the shading here shows that day 5 root mean square forecast error of the forecasts of QG model states by the QG model itself. So it's a perfect model forecast situation. The low value of the forecast error in some region of the phase space means that the initial states whose projections onto the EOF1 and EOF2 plane fall into these regions are characterized in 5 days by the low root mean square forecast error. Okay? Note that this actual well-forecasted states won't be coinciding with those initial states, right, but will be displaced with respect to initial positions according to the evolution of the model trajectories. And what we'll show is that those initial conditions end up in 5 days in the regime regions and stay within the regime regions for at least 5 more days. Okay, what's shown on the, that's why we will call these regions of the low RMSD the regime precursor regions, because the regimes follow the initial conditions that are in these precursor regions. The left panel here shows is analogous to the right panel, I'm sorry, is analogous to the left panel, but shows the 10-day distribution of the 10-day root mean square forecast error. And it has a similar distribution to the 5-day forecast error. It seems plausible, therefore, that the regimes 1 and 2, which we will call the predictable regimes, arise because the trajectories initialized in the precursor region enter the regimes in 5 days and then stay within the regime regions for at least 5 more days while maintaining the low spread, and this makes them predictable. This is directly confirmed by computing the conditional probability distributions of the states of 5 days and 10 days prior to the occurrence of the regimes. And these conditional probabilities have maxima in the regime precursor regions, which directly confirms that initializations in this regime precursor regions end up in the regimes in 5 days and stay there up to 10 days. The same kind of conclusion can be illustrated by looking at the bunches of trajectories initialized in various locations in the phase space. This figure shows the examples of initializations in the regime precursor regions, regime 1 on the left and regime 2 on the right, and it shows the distribution of model states in 1, 5, and 10 days after initialization. And what we can see that by day 5, the cloud of model states reaches the regime regions and stays within those regime regions up to 10 days while maintaining relatively low spread. On the other hand, if we initialize in the phase space region that's characterized by the high root mean square forecast error, that the cloud of model states moves toward the climatological mean much faster and spreads out much quicker. Initializations behind the unpredictable regime 3 have intermediate characteristics. It slows down a little bit within the regime region by day 5, but then does not continue to stay within the regime region, but instead goes toward climatological mean and spreads out somewhat faster than in the case of the predictable regimes. Therefore, what we showed is in the quasi-geostrophic model considered, some of the nonlinear regimes are indeed characterized by predictability characteristic and by enhanced predictability compared to the other states. The existence and predictability of the regime depends on a number of factors, and these factors were considered in a complementary study by John Peters and myself, which John presented yesterday. In a nutshell, the regime predictability, or the regime existence, has to do with primarily slowing down of the model trajectories in the regime regions. Furthermore, the regimes 1 and 2, the predictable regimes, are predictable for different reasons. In particular, regime 1 is predictable because of the low value of the multiplicative noise within this, in the neighborhood of this regime, but regime 2 actually depends on the anomalous convergence of the phase space mean velocities in the regime regions, while regime 3 is unpredictable because both the multiplicative noise and phase space velocity convergence are high within this regime region. Thank you.
I'd like to thank all of the speakers of this session, first of all. So let's do that. Thank you very much for some excellent talks. I'm sorry to tell all of the people who have just come in that this session is now closed. However, we will continue at 1:40 in the poster sessions outside in NG 33B, Current Issues in Stochastic Modeling of Weather and Climate. Thank you very much.